Alright, this is section 4.3, problem number 9. We're looking at f of x equals sine of 8 of x, and we're trying to find the extreme points, critical points, local max, local min, etc. And so the first thing I like to do is I like to graph a typical sine of theta graph, which of course goes through its cycle of 0 at 0, pi halves at 1, pi at 0, 3 pi halves at negative 1, and 2 pi at 0. So it cycles and it continues that cycle. You may wonder, what does the 8 do when it's multiplied to the x? So let's experiment around a little bit. Let's plug in theta equals, or let's plug in, let's say that we're going to plug in x equals, let's say x equals pi eighths. Yeah, so we'll do x equals pi eighths. Well, 8 times pi eighths, so if x equals pi eighths, and we plug that in for f of pi eighths, we're going to get sine of 8 times pi eighths. The eighths are going to cancel, and now you'll notice that this is sine of pi, which is sine of pi is, of course, 0. So the point being here is that this 8, it actually increases your frequency. And so instead of all of these being like our regular sine of theta graph, now they're all going to be, all of these points are going to be divided by 8. And you can graph this for yourself. So if this is the original sine graph, this is the sine of 8x graph. And its values, it starts at x equals 0, just like the last one. Then it goes to x is pi halves divided by that 8, which is pi 16ths. And then we go to pi divided by 8 is pi eighths. Then we go to 3 pi 16ths, 3 pi 16ths, and then we go to 2 pi divided by 8, which is pi fourths. And so this is now our sine, this is our sine of 8x, and if we were to graph it on our original graph here to show scale, you would notice that if there's one cycle here with sine of 8x, there's actually 8 cycles. And I didn't draw it perfectly, but the frequency increases drastically. And you'll notice that by pi fourths, we've gone through one cycle. Well, pi fourths on this graph is just there. So this whole one cycle for this graph happened between 0 and pi fourths. So we've pushed the graph together and made it have a much higher frequency. And so we're going to use this graph that we've figured out using some techniques. In this case, dividing all of the typical values by 8 to find our first cycle. And you'll notice that, pleasantly enough, they asked us to evaluate this between 0 and pi fourths. And now we can tell that one full cycle is actually 0 to pi fourths, so that's nice. So this is our sine of 8x graph. Now, if we want to find the extreme values, we're going to look for when f prime of x equals 0. F prime of sine f prime of x of sine of 8x is going to be cosine of 8x times the derivative of the inner function 8x. So f prime of x equals 8 cosine of 8x. And we're curious because you remember, for a few of the extreme values, like this one for example, and this one for example, the slope will be equal to 0. And the derivative gives us what the slope is at any given point, at any given input. So if we want to find these values, we would set the slope equal to 0 and solve. So we'll divide 8 on both sides. We'll end up with 0 equals cosine 8x. Then we're going to use the arc cosine function on both sides, and we'll end up with arc cosine of 0 equals 8x. And at this point, this right here, we can just deal with the traditional cosine function. Then we'll divide those values by 8 to solve for x. But the traditional cosine function starts at 1, drops to 0 at pi halves, drops to -1 at pi, goes to 0 at 3 pi halves, and then ends at 1 at 2 pi all over again. So this is 2 pi, 3 pi halves, this is pi, pi halves, and 0. And so what we're curious with arc cosine, with cosine, we're given an input and we're asked for an output. With arc cosine, we're asked for an output and then we're given an input. So essentially, we're asking here, when is the output 0? So arc cosine of 0 is, when is the output 0? For what input would our output be 0? Well, our output is in the y direction, our range, and the output equals 0 at pi halves and 3 pi halves in this domain that we've chosen. And so we can write here that arc cosine of 0 is pi halves and also 3 pi halves. And in fact, there are infinitely many points on the cosine graph that equal 0, because the function keeps going. But we're choosing it in a selected range. So if this equals 8x, we can divide both sides by 8, and we'll end up with pi 16ths, and 3 pi 16ths is equal to x. So these are a couple of our extrema. And look, we look back at our sine of 8x. Look, 3 pi 16ths is precisely where one of our extrema is, or our critical points, and pi 16th is exactly where another one is. Now, unfortunately, setting the derivative equal to 0 only solves part of the problem. It gives us the extrema when the slopes are 0. But when you cut your domain, so in other words, we're not looking at infinity, at a domain of infinity, we're looking between 0 and pi fourths. Well, that changes things up because the domain endpoints can also be extreme values. So if we look here and here, those are also going to be extreme values. And locally, this would be considered a local maximum, correct? And this would be considered a local minima. What would this be considered? Or what would this be considered? And remember, locality, we're looking at what's around it and relating it to what's around it. So if you look at pi fourths, when x equals pi fourths, it looks greater than everything that's around it in our domain. So we would call this a local max. And conversely, over here, if we look at the things around x equals 0, its y output is minimum compared to everything else around it. So we would call this a local min. And pi 16ths we would call local max. And 3 pi 16ths we would call a local minimum. Alright, so that's kind of how we can use graphing the function and manipulating the function to kind of help us see what's really going on here. And so we were able to solve algebraically for the critical points that had a slope of 0. That's what we did here. But it excluded 2 other critical points based on our domain endpoints. And so if this were to ask for our maximums would occur at, let's do the ordered pair. And so with the ordered pair, our max would be at 1's at pi 16ths. And its output, because sine of 8 times pi 16ths, that's sine of pi halves, which is 1. And then our other maximum would occur at pi fourths, our local maximum at pi fourths. And if we plug in pi fourths to 8x, pi fourths, that's going to give us 2 pi, and sine of 2 pi is 0. And so those are our 2 local maxes. Here's our local min. Our local minima is at, well, one of them is at x equals 0, and the output there is also 0. And then one of them is at 3 pi 16ths, and its output is minus 1. So it is rather goofy that, for example, at pi fourths, our output is 0. At 0, our output is 0. But in the definition of locality, one of them is a maxima, and the other one is a minima, even though they have the same output. It's all about the surroundings. And so I hope this was helpful. Definitely using graphing calculators, using knowledge of trig, can often save a lot of nasty algebra. And remember that with trig functions, they are infinite. And so it's your job to figure out what are the boundaries, because, like, for example, your calculator will just give you the first point at which cosine equals 0. It won't give you the second point, the third point, the fourth point, because cosine equals 0 an infinite number of times. So that's what makes these problems kind of tricky. Hope this helps, and I'll see you next video. Thanks.